We've been looking at exponential functions and now logarithmic functions, and we're now looking at the properties of logarithms. So let's first review or recall what a logarithm is. And so we have our definition here, but a couple of things have to hold in order for us to use this definition. And so the following have to hold: A, B, capital M and N, and R, all real numbers. A has to be greater than 0, A can't be 1, B has to be greater than 0, B can't be 1. And what we're taking the log or natural log of, that value has to be bigger than 0. And so if those stipulations hold, we have if y equals log base a of x, if and only if x is equal a to the y. So a logarithm, again, is just an exponent. What are we going to raise that base to? What exponent are we going to raise that base to get us back, in this case, x? And we can go back and forth between logarithm and exponential functions by using this definition. So properties of logarithms, the following hold. So if you have some log of a of 1, this is equal to log base a of 1 is equal to 0. Which, if you think about it as with exponents, that makes sense, right? So if I just look at log base a of 1, this is saying a to what power equals 1? Well, a raised to the 0 power is 1. The next one we have is log base a of a is equal to 1. Again, if we think about this by definition of exponents, what would we raise a to get back a? Well, we would raise a to 1 to get back a. Here we have a log base a of m raised to the r power. This is the same thing as r times log base a of m. Okay. And we'll maybe prove that later. But basically, and this is something that's really helpful, and this is what's going to help us solve exponential equations where you have a variable in your exponent. We can bring our exponent down in front of our logarithm. And this one, a raised to the log base a of m is equal to m. So let me actually show you this one. A raised to the log base a of m is equal to m. So by definition, a function and its inverse, if we take the composition of those two, this is equal to x. If we let how about f of x equals a raised to the m power, and f inverse of x equal log base a. And I'm off a little bit because I called it x, not m. So let's call this x. And then let f inverse of x be log base a of x. Okay, so now if I take the composition of those two functions, f of, so I'm plugging in my log base a of x, wherever I see an x and f of x. And so if I do that, I get here a raised to the log base a of x. Excuse me. And by definition of a function and its inverse, we know that taking the composition of the function and its inverse is just equal to x. Where if we let x equal m, then we could say, well, then a log base a of m then has to equal m. Okay. So we just showed why that is true by a proof. So looking at log base a of a raised to the r power, this is also equal to r. So we can think about that as definition of a function and its inverse, just like we just did, or think about it with the exponents. So if we have log base a of a raised to the r power, so this is saying a, our base a, is raised to what power to give us back a raised to the r power? Well, this has to be r. A to the r is the same thing as e raised to the r times the natural log of a to the r. If we have log base a of a multiple of two things, m times n, then we can rewrite this as a string of simpler logs. If it's multiplication in between, then it's addition. So log base a of m plus log base a of n. If we have log base a of m divided by n, then we have log base a of m minus log base a of n. If m equals n, then we can say that log base a of m has to be equal to log base a of n. So taking the log of both sides of our equation. If we have two logs are equal to each other, same base, then we can say that m is equal to n. And last one, change of base formula. So in our calculators, and that might have changed with technology, but with our calculators, it only does base 10 and base e. And so if we have another base and it's not solvable without a calculator, then we can rewrite our log to be a base that the calculator owns or uses. So we have log base a of m is the same thing as log base b of m all over log base b of a. Okay, so a lot of different properties. So let's look at these properties and do some examples. So our example here says use properties of logarithms to find the exact value of the expression. And so we have log base 7 of 7 raised to the 29th power. So again, we're thinking, what are we raising our base to? 7, to get back this 7 raised to the 29th power. Well, we would have to raise 7 by the 29th power to get that back. And so this is equal to 29. What if you had natural log of e raised to the negative 4th power? So recall the natural log is log base e. So if it helps you write it out that way. So log base e of e raised to the negative 4th power. So this is saying, what are we raising this e to get back this e to the negative 4th power? Well, we would have to raise e to the negative 4th power to get that back. So this is equal to negative 4. the other ones here, okay, we have log base 5 of 35 minus log base 5 of 7. So if we have subtraction in between two logs that have the same base, we can rewrite this as a single log. So we can rewrite this as log base 5 of 35 divided by 7. Well, if we simplify that, and we would get log base 5, 35 divided by 7 is 5. So this is saying we're going to take 5 to what power to get back 5? Well, we'd have to take 5 to the first power to get back 5. So this is equal to 1. Okay, so it's important to be able to take a ugly looking logarithm and rewrite it as a sum and difference of simpler logs. And so let's say that you have here that you have log base 5 of the cubed root of x squared plus 1 all over x squared minus 1. And these are for values of x greater than 1. So the direction says write each expression as a sum and difference of logarithms, express powers as factors. Okay, so I have division here, and so we can rewrite this. If we have division, we can rewrite it with a minus in between the two logs. And so we're going to take the log of the numerator. And as I rewrite the log of the numerator, I'm going to rewrite this without a radical. So it's important to be able to go back and forth between radicals and rational exponents. And so recall, if you have b raised to the m divided by n power, this is the same thing, the nth root of b raised to the m. And so here, my index of my radical is 3. And so I'm going to take x squared plus 1 and raise this to the 1/3 power. And then we have minus the log of x squared minus 1. So we can rewrite this. We can bring our 1/3 down front. And this will give us log base 5, gives us 1/3 times log base 5 of x squared plus 1 minus log base, there should be a 5 here, base 5 of x squared minus 1. I noticed that x squared minus 1 factors, so we could technically rewrite that. So 1/3 log base 5 of x squared plus 1 minus log base 5 of x minus 1, x plus 1. Multiplication in between, when we have a log, we can rewrite that with addition. So we have, let's bring it down, 1/3 log base 5 of x squared plus 1 minus, if I rewrite this as addition though, this minus has to go to both. And so this would be log base 5 of x minus 1, then plus, because of the multiplication, log base 5 of x plus 1. So the negative gets distributed. And then we've gone as far as we can. So 1/3 log base 5 of x squared plus 1 minus log base 5 of x minus 1 minus log base 5 of x plus 1. Okay, So we just rewrote this logarithm as a sum and difference of simpler logs. So I just want to state this, but if you have log base b and you have a plus or minus, so you have more than one term in there, this does not equal. Don't think of this as distributing your log base b. So don't do that. I just wanted to bring up an example from my calculus class where we're using this logarithmic differentiation to help us take something that's really ugly and would be hard to find the derivative of, which you'll learn what that means later. But we can use rules and properties of logarithms to rewrite it. So for instance, and let me just pull this and then let's look at finding the logarithm of this. Okay, so let's look at this. So let's just say that we had this function here and let's just rewrite it. So let's say we wanted to look at this and have this as the natural log of the square root of x plus 1 to the 10th all over 2x plus 1 raised to the 5th power. And let's use properties of logs to rewrite this as a sum and difference of simpler logs. So first thing we want to do is we want to rewrite the square root as a rational exponent. So we have x plus 1 raised to the 10th all over 2x plus 1 raised to the 5th power. And this is all raised to the 1/2 power. We now can use properties of logarithms. We can bring our exponent down front in front of our log. So we have here 1/2 natural log of this x plus 1 to the 10th all over 2x plus 1 to the 5th. So now we have division. Division tells us that we can break this down as subtraction. So we have 1/2. We need a bracket here. The natural log of the numerator. So x plus 1 to the 10th. And then minus, because of division, the natural log of 2x plus 1 to the 5th. So we're almost there. Now I can take my powers and we can bring them down. And so we have 1/2 all times 10 times the natural log of x plus 1. Minus, we can bring the 5 down, 5 times the natural log of 2x plus 1. We can distribute our 1/2 to each term. So if we look at 1/2 times 10 natural log of x plus 1, well, 2 goes into 10 5 times. And so we're left with 5 natural log of x plus 1. 1/2 times 5, so minus 5/2 natural log of 2x plus 1. Now I need to be able to go the opposite direction. So having multiple logs, a string of logs, and rewriting it as one log is really helpful. And that's going to help us later on today when we're looking at solving logarithmic equations and where we have more than one log in that equation. So first thing that you need to do is we need to get rid of, excuse me, any coefficient in front of our log and rewrite it as the exponent. And so doing this, we would have log base 5 of 3x plus 1 all cubed minus log base 5 of 2x minus 1. This is all raised to the second power minus log base 5 of x. So let's move left to right, and moving left to right, this minus right here tells me to rewrite it as one single log. So log base 5 of my numerator, it's going to be the first log, 3x plus 1, quantity cubed, all over this 2x minus 1, quantity squared. And then minus this log base 5 of x. Okay, so again, minus tells us division. So this is going to give me a complex fraction, fraction within a fraction. So this gives me log base 5 of this 3x plus 1 quantity cubed all over 2x minus 1 quantity squared, all divided by x. Well, let's think of that x as x over 1, so we can invert multiply. So this is log base 5 of 3x plus 1 cubed all over 2x minus 1 quantity squared times 1 over x. And we're pretty much done. So this is the same thing as log base 5 of 3x plus 1, that quantity is cubed, all over, I'm just going to put the x first, x all times 2x minus 1 quantity squared. So we have log of x squared plus 2x minus 3 all over x squared minus 4 minus log of x squared plus 7x plus 6 all over x plus 2. And it wants us to rewrite this as a single log. I noticed that this minus in between, that's going to tell us to use division. But I also noticed that we have polynomials in here that could be factored. And so if we look at our numerator here, x squared plus 2x minus 3. We can factor this. So let's do this while we're rewriting it. So this factors as x plus 3 all times x minus 1 divided by, and my denominator here is a difference of squares. So x minus 2, x plus 2 minus, but minus tells us to divide. And if we start factoring our numerator, so x squared plus 7x plus 6, this factors as x plus 6 all times x plus 1. It doesn't factor as much as I wanted it to, but that's okay. All over x plus 2. So division with fractions, we're going to rewrite it as multiplication. So we have log of x plus 3 times x minus 1 all over x minus 2 times x plus 2 times x plus 2 all over x plus 6, x plus 1. So I notice that my factor of x plus 2's cancel. And so we can rewrite this as log of our numerator, which would be just the x plus 3, x minus 1, all over our denominator, x minus 2, x plus 6, all times x plus 1. So we just rewrote this as a single log in simpler form. So our next example says show that log base a of the square root of x plus square root of x squared minus 1, and then plus log base a of the quantity x minus the square root of x squared minus 1, and that quantity is equal to 0. So let's rewrite this. I see that we have this plus here, and so that's telling me multiplication. And so we can rewrite this as a single log, and this is log base a of the square root of x plus the square root of x squared minus 1, all times x minus and I rewrote two separate problems, so let's get rid of that square root there. So x plus the square root of x squared minus 1. And so all times x, all time minus the square root of x squared minus 1 is equal to 0. So notice what we're multiplying by our difference of squares. And so we can just square the first piece, x times x is x squared, minus the square of the second piece. Well, if I square that square root, then I'm just left with what's underneath the square root, which is x squared minus 1. But I need parentheses around that whole radicand. Now let's distribute our negative. And so we have log base a of x squared minus x squared minus 1 plus 1 equals 0. Those x squares cancel, so we have log base a of 1. We're showing that that's equal to 0. Well, it's true, right? If I rewrote this in exponential form, a to the 0 power is equal to 1, which it is. Okay, so one other type of problem, which is change of base problem. So we're going to use the change of base formula and a calculator to evaluate each of the following logarithms. So let's say that we had log base 5 of 18. So we just looked at the change of base formula at the beginning of class. Which says if you have some log base b of a, this is equal to the log of a all over the log of b. Or we can say this is the natural log of a over the natural log of b. So we can rewrite this. This is the same thing as the log of our new base. So we could just do base 10 of 18 divided by log of 5, which should give us the same thing as if we looked at the natural log of 18 divided by the natural log of 5. So this piece is a calculator exercise. And so you're putting in log of 18. Divide that whole thing by log of 5. And it said round 3 decimal places. So this is approximately 1.7958. So that 8 is going to round that up to a 6. So 796. So let's do one more change of base. So if we had, how about log base pi of the square root of 2? So log with no base written as base 10. So this could be the same thing as a log of 2 over the log of pi, which should be the same thing as the natural log of root 2 over the natural log of pi. So log square root 2 divided by log pi. Rounding 3 decimal places, well, we get 0.3027. So that 7 is going to raise that 2 to a 3. So we have 0.303. Okay, so that is the 6.5 in our textbook, properties of logs. So the following direction says use properties of logs to solve the following and do it without a calculator. And so let's first maybe set x equal to this log base 2 of 6. And so if we rewrite this in exponential form, this is the same thing as 2 raised to the x is equal to 6. Let's do the same thing with the other logarithm. And so let y equal log base 6 of 8. And let's rewrite this in exponential form. So this is 6 raised to the y power is equal to 8. But over here, it tells me what 6 is equal to. So let's go in and let's replace what 6 is with 2 to the x. So instead of 6 here, I'm going to rewrite this as 2 raised to the x power raised to the y power is equal to 8. So rules of exponents, power to power is multiplication. So we have 2 raised to the x times y power equals, well, I want to use the rule that if I have the same base, I can set my exponents equal to each other. So we can rewrite 8 as 2 cubed. And so x times y has to equal 3. But x, we had chose to be log base 2 of 6 times y, which we had chosen to be log base 6 of 8. So x times y, which is log base 2 of 6 times log base 6 of 8 has to equal 3. So our solution is 3.